This visualization represents a silent failure cascade in a complex multi-agent system. When deploying autonomous agents to production, you are no longer dealing with simple linear code execution. You are managing non-deterministic multi-step reasoning loops. And when one of those loops seizes up in production, the entire system halts. The immediate instinct for engineering teams is to rely on standard black box prompt logging, but dumping flat text logs of the inputs and outputs provides zero actionable diagnostic traces. You can see that the agent failed, but you cannot reconstruct the precise sequence of tool failures or model hallucinations that caused the root error. Legacy distributed tracing frameworks attempt to map these executions, but they rely on synchronous network calls. In real-time inference environments, forcing the main application thread to wait for a logging server to acknowledge a telemetry receipt introduces unacceptable I/O blocking and massive latency spikes. To safely run agents at scale, the architecture requires a strict decoupling mechanism. Telemetry capture must be separated into non-blocking, hierarchical execution trees that process entirely out of band from the main user conversation. The open-source client implementation of this architecture is the LangSmith SDK. It operates as a telemetry and evaluation harness specifically engineered to bypass these latency bottlenecks. Observability in the AI era cannot be treated as passive logging. By structuring agent data effectively at runtime, that exact same telemetry becomes the structural prerequisite for runtime verification, continuous regression evaluation, and self-improving agents. Looking at this diagram, a flat sequence of server logs structurally transforms into a directed acyclic graph, or DAG. Agent execution is inherently hierarchical. A main task spawns a subagent, which then executes a search tool, which feeds context back into an LLM. The SDK reconstructs this execution path using the @traceable decorator. When a developer applies this to a function, it instantly generates a unique run ID for that specific execution instance, tracking it as a parent node with zero manual boilerplate. Under the hood, this relies on Python's contextvars. This mechanism allows ambient execution context, whether a thread local or within a coroutine, to be read directly from memory. Because of these context variables, a developer never has to manually pass span identifiers down through their code. When a nested child function executes, it invisibly reads the active context and automatically inherits its parent's run ID. This inheritance links every subagent delegation, prompt payload, and tool output together. The result is a unified data object called a RunTree, which preserves the exact temporal ordering and exact token consumption at every specific branch of the graph. Older distributed tracing tools require developers to manually instrument every single span, cluttering the business logic with heavy network tracking code. By abstracting context propagation, engineering teams gain full visibility into intermediate reasoning steps, individual token costs, and exact latency timings, while keeping the underlying application code entirely pristine. Capturing this data introduces a severe latency challenge. Streaming LLM responses fire off thousands of rapid token chunks. Intercepting that density of data over a network connection will inevitably break the main application's event loop. This data flow diagram shows the SDK's interception layer. Using a function called wrap_open_AI, the SDK transparently monkey patches the underlying API clients. It sits directly over the data stream, capturing raw prompt payloads and tool definitions as they happen. Rather than pinging the server for every generated word, the wrapper aggregates these token deltas locally. It holds them in memory and only finalizes the complete run record when the LLM stream explicitly terminates. Once finalized, the serialized RunTree payload is pushed into an in-memory queue within the asynchronous transport layer. The main execution thread immediately moves on, bypassing HTTP wait times entirely. The SDK scales this transport layer through two distinct mechanisms: standard background thread workers managed by the client object, and non-blocking asynchronous event loops handled by asynchronous client, engineered specifically for high concurrency environments. There is a calculated engineering trade-off here. During bursts of high-volume tool execution, if the network connection to the ingestion server experiences severe latency spikes, these in-memory queues will consume significant local RAM to hold the buffered data. However, transactional client buffering ensures that transient network disconnects or telemetry payload sizes never interrupt the real-time user conversation. In production, observability immediately runs into a strict enterprise regulatory constraint. Raw agent prompts inherently contain personal identifiable information, proprietary database identifiers, and occasionally raw passwords. Transmitting these raw payloads over a network to an external ingestion server explicitly violates stringent HIPAA and GDPR frameworks. To solve this, the SDK enforces privacy at the edge. This diagram shows the create anonymizer function acting as a strict middleware interceptor gate before any network request is initiated. Developers configure custom string node replacements or callable rules inside this middleware. As the payload passes through, sensitive data fields, credit cards, emails, API tokens, are instantly overwritten and masked with placeholder tags before the payload ever exits the local network boundary. By decoupling client-side sanitization from server-side ingestion, all private credentials remain securely locked within the host organization's internal security policy. Implementing edge-based data redaction neutralizes the primary risk of capturing vast amounts of telemetry, transforming observability from a potential security liability into a highly compliant, auditable asset. Once system telemetry is securely captured and stored, it transitions from passive observation to active validation. Production traces are leveraged to curate immutable, versioned benchmark datasets. Looking at this evaluation matrix, we see the evaluate function in action. This is the SDK's engine for running deterministic offline regression tests. A versioned dataset is fed into a parallel worker pool, simultaneously stress testing multiple variations of a target agent graph. Across these parallel async worker pools, custom evaluators and LLM as a judge models assess the outputs, verifying that prompt revisions actually improve reasoning rather than degrading it. These evaluators emit highly structured evaluation result objects. They deliver exact numerical scores, Boolean pass-fail flags, and diagnostic strings, providing immediate mathematical proof of any performance regressions. Beyond logical regression, engineering teams face a final operational security challenge, evaluating autonomous agents that are designed to generate and execute untrusted code. You cannot run untrusted LLM-generated shell or Python scripts directly on a host machine. Instead, the SDK utilizes a sandbox client to provision remote, isolated micro-VMs. The SDK manages these environments over secure WebSockets and mutual TLS. The communication layer guarantees that the agent's code executes with configurable memory limits and network proxies, remaining entirely quarantined from the main host runtime. Combining systematic parallel evaluation with secure remote sandboxing completes the evolution of AI development. It replaces experimental prompt hacking with rigorous, verifiable software engineering. This diagram maps a production agent's lifecycle. A user prompt initiates a context-propagated @traceable DAG, filtering into a local buffer cleared by an asynchronous flush. The flow then forks into 3 secured pipelines: edge data redaction, offline evaluation, and remote sandbox execution. With this topology, teams continuously ingest operational data, rapidly detect prompt regressions, and safely evaluate model migrations before pushing updates to the public. This systematically displaces ad hoc print debugging and standard distributed tracing tools, which fundamentally fail to provide the token and prompt introspection required for language models. The LangSmith SDK establishes the baseline for modern AI deployment. Deploying autonomous agents successfully requires non-blocking hierarchical execution trees, continuous dataset evaluation, and strict micro-VM isolation.